Verilog looks deceivingly familiar. When it was introduced in 1984, the creators gave it a syntax that closely mirrored the C programming language to help software engineers adapt quickly. You see if statements, for loops, and while loops, and your brain assumes you are writing a standard computer program. But that syntax is a trap. C code is a sequence of instructions fed to a single CPU, executed one line after another. Behavioral Verilog is a textual representation of physical hardware. A traditional software program reads from top to bottom, but an electrical circuit doesn't process lines of code. When power hits a physical circuit board, millions of transistors and logic gates power up, fracturing outward to interact simultaneously. Applying a sequential software mindset to a hardware description language creates unpredictable race conditions and catastrophic mismatches between what you simulate and what the compiler actually builds in silicon. To understand how this code actually operates, we have to look at the core architecture of the Verilog simulator itself. The simulator relies on the discrete event execution model. This is an invisible engine that tracks time, schedules upcoming changes, and processes simultaneous hardware signals without forcing them into a single file line. We are going to map exactly how this engine works by dissecting procedural blocks, exploring how timing controls route data, and resolving the vulnerabilities that cause synthesis compilers to fail. Mastering register transfer level design requires abandoning the illusion of sequential software. You are not writing a script. You are manipulating time and concurrency. The highest level of behavioral abstraction in Verilog is the procedural block. Think of it as an independent container for a standalone hardware process. Every simulation begins at a primordial starting condition, known as time zero, or t equals 0. Unlike C functions waiting to be called, all declared Verilog procedural blocks wake up and trigger concurrently at time 0. There are two main types. The first is the initial block. It runs its statements exactly once, then terminates. Because physical hardware rarely runs a process just one time, initial blocks are exclusively used in test benches to generate stimulus waveforms. The second type is the always block. When an always block reaches the end of its code, it immediately reschedules itself and starts over, executing continuously for the entire life of the simulation. These blocks do not wait for one another at all. They operate as free-running, entirely independent processes evaluating in complete parallel. The baseline state of HDL simulation is massive, uncoordinated concurrency. Designers must use specific tools to force strict order onto the system. An infinitely looping always block will completely lock up the simulator. We need internal routing mechanisms to regulate exactly when these independent blocks evaluate. Timing controls act as execution barriers, suspending a block's activity until a required condition is met. The most basic is delay control, represented by a hashtag. Writing #5 suspends execution for exactly 5 simulation time units before allowing the process to continue. Event control, represented by the @ symbol, suspends execution until a physical change occurs in a targeted variable, like waiting for the positive edge of a clock cycle. To prevent accidental omissions, the implicit event expression automatically senses changes in any variable read within the block. Once past these timing barriers, we must organize the actual lines of code. We use block statements, grouping mechanisms that dictate how multiple operations interact. The sequential block uses begin and end. Inside, statements execute strictly top to bottom. By contrast, a parallel block uses fork and join. All statements initiate simultaneously, exiting only when the longest operation finishes. Verilog allows advanced dynamic control using the disable statement. Upon a system reset, you can command the simulator to instantly abort a named block mid-execution. Timing controls and block statements provide the precise routing logic needed to take wild concurrent hardware models and tame them into reliable, deterministic systems. Even with strict block statements, engineers thinking in C often trigger race conditions when they assign data to variables. The culprit is usually the standard equal sign, known in Verilog as a blocking procedural assignment. A blocking assignment calculates the right-hand side and updates the left-hand target immediately. It physically blocks the execution flow, preventing the simulator from reading the next line. To accurately model parallel hardware, Verilog uses a non-blocking procedural assignment, written as a less than or equal to sign. This relies on deferred execution. The standard defines a two-step evaluation. The simulator reads all right-hand values simultaneously, without halting flow, scheduling them in a temporary queue. It moves directly to the next line. Finally, at the time step's end, the queue releases, updating all targets simultaneously. Non-blocking assignments are essential. They allow us to accurately model the synchronous, parallel state transitions of physical flip-flops without creating artificial software bottlenecks. Simulators track abstract events in time, but eventually this code must face the synthesis compiler, the tool responsible for converting those theoretical events into physical silicon gates. This exposes the inherent danger of the standard Verilog always block. It is a completely generic container. It carries no explicit instructions about what kind of hardware it is supposed to become. Take a standard 4-to-1 multiplexer. A designer might use a standard always block to map the input signals to the output. Looking closely at the sensitivity list on line 7, there is a simple omission. Because the compiler cannot execute a clean combination of inputs, it infers an unintended hardware memory latch to hold the previous state, ruining the intended combinational logic. Traditional Verilog cannot proactively protect you from this. The simulator will run the flawed code without throwing an error, leaving a silent synthesis mismatch waiting in the silicon. System Verilog solved this by replacing the generic always block with 3 hardware-specific blocks. The first is always calm. It replaces manual sensitivity lists with automatic implicit sensing and enforces strict combinational logic rules. If incomplete logic infers a latch, the compiler immediately triggers a warning. The second is always FF. This strictly commands the compiler to model synchronous flip-flops and registers, ensuring sequential memory is only built when explicitly requested. Finally, always latch exists for those rare cases when a designer actually intends to infer internal memory loops. It signals deliberate intent to the compiler. Advanced RTL design requires a dual mindset. You must write code that precisely commands the event-driven simulator to map time, while strictly satisfying the synthesis compiler to map physics.